So today we get to make some pretty pictures. We're going to use that polar coordinate system and some different various functions or equations to make these graphs. First of all, we're going to start out with circles. And we know that if we see an equation of the form r equals a sine theta or r equals a cosine theta, that based on the graphing that we've done thus far with our graphing calculators or Desmos, we're going to get a circle. Okay? In fact, if we get plain old r equals some number, we're going to get a circle. That circle is centered at the pole, but the other ones will be shifted. So when you see r equals a sine theta, think about, first of all, a being the diameter of that circle, and b, if the a is positive, it's going to be symmetric with the line theta equals pi over 2. So it's going to be on what was traditionally the positive y-axis in our rectangular coordinate systems. Okay? And if a is negative, it's going to shift it down and put it where the traditional negative y-axis was. Okay? So think of sines and y's going together. Okay? Cosine, r equals a cosine theta, a is still the diameter, but this time if it's positive, it's symmetric with the polar axis. And so you will see it shifting to the right on that polar coordinate system. And if a is negative with cosine, it's going to shift it to the left in what would be traditionally the negative x-axis on the rectangular coordinate system. Okay? So kind of sketch those graphs for me. And we know a is the diameter, not the radius in this case. And if it was plain old r equals something, then it's just going to be a circle centered at the pole. Bless you. So let's put this into practice. Our first example is going to ask us to graph r equals 6 cosine theta. So we know that because it's cosine, it's going to be along what would traditionally be the x-axis, right? Okay. It's a positive 6, so is it to the right or to the left of the pole? To the right. And what's its diameter? 6. So we want to go from the pole 6 out, and we want to make a circle that has that diameter. I don't usually do it very well the first time around. And that's all there is to graphing a circle. Now, back in the day when I was taught this, we didn't have graphing calculators, we didn't have Desmos, so we had to plug points in and figure out what these points were. And I don't want you to lose track of that. Okay? This is no different than plotting the plug and chug type of thing. But we're learning it a much faster way because we can see patterns and use the technology to help us. So for example, if I were to plug in theta is 0, the cosine of 0 is 1, so 6 times the cosine of 0 gets me r, I'll get 6. So when theta is 0, I'm over here at 6. Okay? What happens when theta is 30? We know 30 is the square root of, the cosine of 30 is the square root of 3 over 2. If I take the square root of 3 over 2 as a decimal times 6, I get 5.2 as my angle, or as my r. So when I am at 30 degrees, I am 5.2 out. Okay? If I've done a good job of graphing this. Then theta is 45. What's the sine of the cosine of 45? Square root of 2 over 2. Square root of 2 over 2 times 6 is 4.2. So at 45 degrees, I'm 4.2 out. And I haven't done a very good job of graphing this. Okay? They were never going to ask you to come up with this table. Okay? This is how we did this 20, 25 years ago. Okay? We don't do that anymore. Okay? At least not in my classroom. I like to use the technology and leverage it, learn the patterns, learn what these things do. But I want you to see where these numbers are coming from and why it looks like a circle. Does that make sense? Should go out to the 6th line. 1, 2, 3, 4, 5, 6. So that's part of where I'm having my problems, is I didn't graph it right initially. Okay, so it should come out to here. Okay, that absolutely helps. Good catch. Okay, and so when I was at 30, I'm at 5.2. So 30 degrees should be 5.2. I still haven't graphed it well. Should be wider. But we're sketching, okay? We want to make sure that you have that general form. Okay, so let's actually plot those points. Yep, at 45, it'd be at about 4. So 45 degrees, we're 1, 2, 3, 4 out. At 60 degrees, the cosine of 60 is a half, so we'll be at 3 out. 1, 2, 3. Okay, now I'm getting a better look of what this is going to look like. Okay, at 90 degrees, I'm at 0. So 6 times 0 is still 0. Then what happens at 120? 120 is a 60-degree angle, so I'm at a half, but I'm at negative 1/2 because cosine is negative in the second quadrant. And negative 1/2 times 3 is, or times 6 is going to be negative 3. So when I'm 120 out, okay, I'm at negative 3, so I have to pull it back, and that's why I'm here. Okay? Then when I'm at 135, that's a 45-degree angle in the second quadrant. Negative square root of 2 over 2 times 6 is negative 4.2. So 45 degrees out, I have to come 4.2 back. I should be here. Yep, should be at 4.2. I did the other one wrong. In a hurry, I've got a lot to cover today. So 3.3, 4.2. Okay, at 150, I'm at square root of 3 over 2, but negative because I'm in the second quadrant. So negative 5.2 at 150. And then when I'm at 180, I'm at negative 6 again. Sorry. When I'm at, what was that? Yeah, negative 6. So 180 out, 6 back. So we're completing our circle here. And if I, of course, filled in the gaps and didn't use just the ones that we know, I'd have even more points there, wouldn't I? And then what happens when I get to these other quadrants? Because of the way it works, we'll end up only tracing over it again. Okay? Does that make sense? That's where these things are coming from. But we don't want you to actually have to make a table of values. We want you to recognize the patterns and know how they work. Okay? Questions on this slide? All right, next slide then. Says let's graph r equals 3 times the sine of theta. Okay, so what's my diameter? 3. Okay, which way am I going? Up. So I want to put a point at 3 and then draw my circle. And if you want to be more accurate, you can actually plot points to see how far out you should be. But that's all I'm looking for is a quick sketch. Okay? So far so good? Next one. Negative 4 cosine theta. What's my diameter? 4. Okay. Which way am I going? Left. So 4 from the hole to the left. And then I want to draw what is supposed to be an accurate circle with a radius of 4, diameter of 4. Okay. You guys can handle these? Okay. All right. Tests for symmetry. We'll talk about this. I'm not sure I'm going to test you over it, but I want you to remember it because we have been talking about symmetry tests for a long time. And it's something that could come back and you'll see it again on the final. Not necessarily for these particular graphs, but in general. Okay? So when we're testing for symmetry, when we want to test for the symmetry with respect to the polar axis, which was traditionally the x-axis, We simply replace theta with a negative theta. If we want to test for symmetry with respect to what was the y-axis, or the line theta equals pi over 2, we replace the r with a negative r, and we also replace theta with negative theta. We compare it to our original graph, or original equation, and see if it's the same. Okay? If it's the same, then it is symmetric with respect to theta equals pi over 2. Then, if we want to check to see if it's symmetric with respect to the pole, we have to replace r with a negative r and simplify it and see if we get the original equation back again. If so, it's symmetric with respect to the pole. Okay? You just try them all, exactly. And then that will tell you whether or not it's symmetric with respect to each individual part. Each line, or the pole itself, what would be the origin traditionally. Okay? So here we go. Going to test r equals -2 sine theta for symmetry to see if it's symmetric with respect to first the polar axis, then theta equals pi over 2, and then the pole itself. Okay? Now remember, sine is an odd function. Okay? So whenever we get a sine of negative theta, we're going to change that to negative sine of theta. But cosine was an even function, so if you are doing a test for symmetry with cosine and you have cosine negative theta, that's going to be cosine theta. Okay? Sine and tangent were odds, cosine's an even. All right, so here we go. If we're testing for symmetry with respect to the polar axis, we replace theta with negative theta. So r is going to be -2 times the sine of negative theta. Okay? Because sine is an odd function, whenever we have the sign of negative theta, that becomes negative sine of theta. And a negative times a negative is positive. So r equals +2 times the sine of theta. Is that the same as our original equation? No. So it is not symmetric with respect to the polar axis. Whenever we basically said, let's change this, okay, sine of negative theta, is that an even or an odd function? It's an odd function, so we can change that to negative sine of theta. Okay? So because our equation after we simplified it is not the same as our original, we know that it's not symmetric with respect to our polar axis. Now let's check and see if it's symmetric with respect to the line theta equals pi over 2. To test that, we're going to replace the r with the negative r and the theta with the negative theta. So it's now negative r equals -2 times the sine of negative theta. And then we simplify. Our negative r will be -2 times the sine of negative theta, since it's an odd function, is going to be a negative sine of theta. A negative times a negative is positive, right? So if negative r equals 2 times the sine of theta, and I want to get the r to make the equation look like the original, r will be dividing by a -1, -2 sine of theta. Does this match my original equation? Yes, so it is symmetric with respect to theta equals pi over 2. Okay. Last test, we're going to check to see if it's symmetric with respect to the pole. That means we simply replace negative r, or r with negative r. So if we do negative r equals -2 times the sine of theta, and we simplify that, we're going to divide by a -1. r becomes a positive 2 times the sine of theta. Is that equal to our original equation? Nope. Not symmetric with respect to the pole. What was traditionally the origin? It is possible for it to be symmetric with respect to all. For example, a circle that just has r equals 16. Okay, that would be symmetric with respect to all three. Okay. Other questions about this slide? And let's see why that's the case. Think about r equals -2 sine of theta. What is our diameter here? 2. Okay. So what's happening is we are moving to which way? Down. Okay. So we would be 2 down. And does it make sense if I draw this right? A little high. Does it make sense that this is not symmetric with respect to the polar axis? It doesn't open evenly above and below what would traditionally be the x-axis, right? Okay. Is it symmetric with respect to the origin or the pole? No. Okay, because it's not opening evenly around it. But what about the line y equals pi over 2? Yeah. Or r equals pi over 2. But theta equals pi over 2. Okay. Everybody good so far? All right. Next one. Limaçons. Okay. Now this is where I had a little fun because I went to Merriam-Webster's dictionary, and I don't know if I have the ability to play this without speakers. You may not be able to hear it. Limaçons. I don't think I have my volume up. And if you have a chance to watch this later, hopefully it will record it. Well, I think I'm as high as it goes. For some reason, I was having trouble with my audio card on Friday. Anyway, it's pronounced Limaçon. It sounds at least the French pronunciation of it. Okay, and it rhymes with papillon. Okay, which is the French word for butterfly. Okay, which is the name of our town. So, but if you have a chance, play it and it will kind of make sense. All right, so on our videos that we watched on Friday, she talked about limaçons, okay, having either an inner loop or a dimple, or a cardioid, or a dimple, or convex, okay? And we're going to talk about those and take notes on those. All right, so limaçons are of the form r equals a plus or minus b times the sine of theta, and r equals a plus or minus b times the cosine of theta. The ratio of a over b is important because it determines the shape of our limaçon. Okay. A over b less than 1 makes an inner loop. And an inner loop, if we were talking about the sine, for example, would look like this. Potentially. Okay, depending on what a and b are. Okay. If a over b is equal to 1, then we get a cardioid. Cardioid looks like a heart. So if this was in the shape of a sine, and we know sine usually is when it's positive opens up here, a cardioid would look something like this. Kind of comes to a point. When a over b is between the numbers 1 and 2, then we get a dimple. And a dimple looks something like this. It's just an indentation. It doesn't come to a point. And finally, when A over B is greater than or equal to 2, we get a convex Limaçon. And that looks something like this. It's kind of just flattened out. Sine versus cosine tells you which axis it's going to be on. When you add A and B, you get the length of your main axis. A is the length of the opposite axis. How far away do you go on each side? And A minus B is your lower point. How much do you indent? Where does that loop go? How much do you bulge out if it's a convex Limaçon? All right, everybody has your notes taken? Got a notes? Okay, away we go. So we're going to graph r equals 1 minus 2 times the cosine of theta. So sine or cosine tells us which way it's going to open, right? This is a cosine, so we know it's going to go horizontally, okay? Negative in front of the cosine means, yep, kind of coming on this side, okay? Then we know we have an A and a B. What's A? And what's B? And don't think about the negative so much, just think of it as 2, okay? 1 over 2. We're not worried about whether it's negative a half or positive a half. We're just stripping those coefficients off, ignoring the signs, okay? So we've got 1/2. Where does 1/2 fall in our range? Less than 1, right? So what kind of a Limaçon are we going to get? An inner loop, okay? So we know it's an inner loop. Okay, it's cosine, so it's opening to the left, okay? And next we need to figure out what our stretch is. How far are we going on this axis, on what would be the theta equals pi axis. So our stretch is going to be A plus B. So what's A plus B? So we know that we're coming from the pole 1, 2, 3 out. That's how far away. And then we say A is going to be our stretch in the opposite vertex, or opposite direction. So how far are we going up and down? 2, a total of 2, right? So we're going to be a total of 2 out. I'm sorry, someone said 2, my fault. Okay, so A is 1. We're going 1 up, 1 down. Okay, and then we're going to do what? Subtract, right? So it's A minus B. Negative 1, right? 1 minus 2 is negative 1. And since A minus B is negative 1, we're coming inside the Limaçon. So this is going to be where our inner loop goes. Okay. So when you would graph this, that's how you do it. Okay. Just one nice fluid from the pole. One nice fluid motion. Okay, to know if it's inner loop or not, we divide A by B, and when it was 1/2, 1/2 is less than 1, so we know it'll be an inner loop. Okay, all about A and B. Okay, Questions about this slide? All right, here comes the next one. R equals 2 plus 3 sine theta. Okay, we have a sine, so we know it's open. It's going which way? From the pole, up and down. Okay, it's positive sine, so we know it's going up. Okay, now we have to figure out A and B. What's A? What's B? So 2 over 3 less than 1. So it's going to be inner loop again. Okay. We need to figure out how big our stretch is. So our main stretch will be A plus B. Okay, so from the pole, we know we're going up 1, 2, 3, 4, 5. And A is our width, right, of our, how wide it's going on our minor axis. So if A is 2, we're going 2 and 2. Okay. Now we need to find out how much we get to go into this with our inner loop. So A minus B. 2 minus 3 is 1, right? Because it's -1, it's going inside. And then we started our pole, and away we go. Because it was an inner loop, it's the ratio of 2/3 is less than 1. Okay, so if it's sine, it's going up and down if it's positive. And if it's negative sine, it's coming down. And if it's positive cosine, it'll go to the polar axis, positive polar axis. Okay? One more? Here we go. All right, now we have r equals 2 plus the sine of theta. Okay? So 2 plus the sine of theta is going which way? Up. Okay? Sine. So up. What's A? What's B? So 2, right? Convex. Okay? So we know we have a convex Limaçon. And how big is our stretch vertically? Yep. So 1, 2, 3. Okay. What is A itself? So we're going 2 on our opposite direction each way. And what's A minus B? +1 this time. So now that's going to bulge us out by 1. Okay. Kind of like a shield because it's convex. Question? Okay, because our A this time was bigger than our B, so and we knew it had to be convex, so we ended up with a +1 that's pushing it out. Okay, not sucking it in this time. Limaçon's okay? All right, next one. Rose curves. These are the prettiest ones. They have the most going on. Okay. Nope, they're not. They're not bad. Easiest are the circles, of course. Okay. Rose curves are of the form r equals a sine n theta. Okay. Very similar to a circle, but now we have done something to our theta. We have a number times that theta. Okay. So as we look at this, our length of our petal is a. So however long that, whatever number is out in front of the sign is going to be how far out we're going. The number of petals is based on what n is. If n is even, you get twice the number of petals. If n is odd, you get that same number. So if n is 3, we get 3 petals. If n is 5, there's 5 petals. But the minute that you get n as an even number, like 2, 4, or 6, you would get 4, 12, or 16 petals. To find where the first petal starts, you're going to substitute a in for r, and then solve for theta. And finally, to know how far to rotate the petal from the first petal to the next, you're going to take 360 or 2 pi divided by the number of petals. So if there were 3 petals, 360 divided by 3 is 120. Every 120 degrees we'll get a new petal. 4 petals, 360 divided by 4, every 90. Okay? See some of you still writing. I'll give you a few more seconds. All right, so here we go. Our first example is going to ask us to graph r equals 3 cosine 2 theta. Okay, r equals 3 cosine 2 theta. So how long is our petal length? Yep. Okay. What's n? So how many petals? Because we double it. It's even, so we're going to double it. Okay, so 4 petals. Okay. Now, to find out where we start, we take r and we replace it with a. So since a is 3, we'll have 3 equals 3 times the cosine of 2 theta. And we're going to solve for theta. Cosine's always going to start on 0. Not necessarily. Okay, sign will change. Okay. So you saw this on Friday when we were watching this. 3 over 3 is always 1. The cosine of what theta gets us 1? 0. Anytime you say 0 equals 2 theta, you're going to divide by 2. So theta is always going to be 0 for cosine if it's a positive. Okay? So that's our starting point. It would still be 0, but it can pull it in the opposite direction. So your first petal can be on this opposite side. Because maybe I'm wrong. No. Right, right. Yes. Okay. So we say, where is the cosine of theta equal to 1? We think about our cosine graph. Cosine starts high, right? That's between 0 and 2 pi. So where is cosine equal to 1 at? Always at 0, right? Okay, so if 0 is equal to now 2 pi, or 2 theta, we divide by 2 to figure out what theta is, and you're always going to get 0. Always 0 for cosine. Nope. Okay, always 0 for cosine. All right, so we're ready to go. We got a petal length of 3, right? So we pull out 3, and we'll have one petal that looks like this. Okay. Now, we need to figure out how far we need to rotate. So 360 divided by the number of petals. How many petals are we going to have? 4. 360 divided by 4, 90 degrees. So we'll have another petal here at 90 degrees. That one doesn't look like 3. Another one at 180. And then one more at 270. Bless you. Okay. Because we had a total of 4 petals. So you take your 360 and divide it evenly among all your petals. That's how much we're rotating from our original. Okay? Other questions about this slide? All right, next one. Now we want r equals 5 times the sine of 2 theta. So how long will my petals be? Good. How many petals will we have? Okay, so we know we have 4 petals. They're 5 units in length, and this is a sine. So we have to figure out where we're going to start. Okay, it won't always be at 0. In fact, it won't be at 0. So we replace r with a. And we solve. So 5 divided by 5 is, okay. So as Peyton was saying, where is the sine in general equal to 1? Always at pi over 2, right? And since it's pi over 2, or 90 degrees, right? Then when we divide by 2, we're going to get 45. Okay, but if it wasn't 2 theta, if it was 4 theta, we're going to take 90 divided by, exactly. Just like with cosine, it's always going to be 0 divided by whatever n is, and 0 divided by anything is always going to be 0. Okay. So our first petal is at 45 degrees, and it's going to be pulled 5 units out. Okay. So we've got one here. Now, how much are we rotating? How many petals do we have? 4. So 360 divided by 4. So we're moving from 45 to 135, 5 units out. Quick sketches is all we're looking for here. Rotate 45 more degrees, we'll be at 225, 5 units out. And then 45 more is at 315. Sorry, 90 more is at 315. And there's our rows. The petals come from the number in front of the theta, and if it's even, we take it times 2. And if it's odd, it's the same number. Okay? Other questions on this slide? Yes?
I forgot how you find out how many petals are.
Okay. To find the petals, you look at the number in front of the theta. It's okay. So number in front of the theta. If it's an even number, then we take 2 times it to find the number of petals. If it's an odd, we just use that number. Okay? All right, next slide. It's okay. There'll be a wet noodle beating after school. I'll let you try and graph this one yourself. R equals 4 cosine 3 theta. So how long are your petals? Okay, so we know we're pulling 4 out. What's n? 3, so how many petals? It's odd, so 3 petals. Okay. Theta is equal to 0 whenever we're dealing with cosine, right? So we're starting at 0. And how many degrees will we rotate for each petal? 120, because 360 divided by the number of petals is the rotation. So we start at 0, pulling out 4. Then rotate 120 degrees. And you should have something that looks like that. Now, actually how this would graph, if you were watching it, actually graph it by point, it would start at 0, and it would loop around, come back, one fluid motion up here, come back, one fluid motion down this way, and then back to 0. So we're kind of cheating by doing our make a petal, make a petal, make a petal. Okay? Lemniscates. Okay? We have about 2 minutes. We should have plenty of time. Won't take much. Okay? All right, lemniscates are of the form r squared equals a squared times the sine of 2 theta, or a squared times the sine of cosine of 2 theta. And this, we're only looking at the lemniscates that are using the 2 theta there. Okay? We have an equation symmetric about the pole if it is a sine, and it's symmetric about all 3 if it's a cosine. It's always going to start at 0 again with cosine, but it will start at pi over 2 with regard to the sine. I'm sorry, pi over 4. So it would look something like this. And they're actually kind of wider than our rose curves. Okay, they kind of look like propellers on a plane. Okay, so 16 is going to be a squared here. Okay, so you need to be careful with this. It's a squared, not a. So our total length out for each one will be 4. So at sine, we're moving 1, 2, 3, 4 out. and 1, 2, 3, 4 back. Always starts at the 45. That's it. All right, I've got 2 sheets for you. I anticipate we'll need a little time to finish up during class tomorrow. So do what you can on this tonight. And I'll see you tomorrow. Sorry, just one quick one. There's the bottom and the top. They're big because they have graphs. Yeah. The lemniscate. Yep, there's 2 pages. Hopefully I counted right.